In the field of acoustics and sound design, technological innovation is opening new frontiers. One of the most revolutionary developments comes from researchers at Penn State University, who have developed an advanced acoustic technique called Audible Enclaves. This technique aims to solve one of the most persistent problems in the design of complex acoustic environments: the management and separation of sounds in shared and dynamic spaces, allowing the customization of the real-time sound experience. What is an audible enclave? An audible enclave, as designed by the research team at Penn State University, is a specific area of an environment where sound is isolated, directed, and optimized in a targeted way. The idea behind the audible enclaves is to create sound islands that allow the customization of acoustics within a larger space, separating precisely the sounds to avoid interference and improve the quality of the sound experience. These sound enclaves are designed to reduce background noise, improve sound clarity, and optimize the quality of communication in complex spaces such as offices, stadiums, theaters, and high-density public areas. The technological revolution. Techniques and approaches used. The Penn State University team has applied some advanced techniques of directional acoustics, computational modeling, and innovative materials to achieve precise control over sound. The main innovations implemented in the audible enclaves include directional acoustics and sound formation. The main innovation of the audible enclaves is the use of directional acoustics, which allows you to focus the sound very precisely on a certain area, limiting dispersion to other areas. Using narrow-beam speaker arrays, the researchers were able to create sound beams that are directed with such precision that they cover only the desired area. This allows a personalization of the acoustic experience within shared spaces, such as theaters or museums, without disturbing other visitors. The technique is based on acoustic directionality, which uses the physical principles of sound waves to target them selectively, minimizing interference. Computational acoustic modeling. Researchers at Penn State University are using advanced acoustic modeling algorithms to simulate and optimize sound behavior in complex environments. Acoustic modeling can predict how sounds propagate in a three-dimensional space, and how the surfaces, materials, and geometry of the environment affect sound. Thanks to this advanced simulation, it is possible to design and optimize the acoustics of the enclave before its physical realization, ensuring that the sound behaves as expected. Sound absorption and sound diffusion technologies. The audible enclaves are not limited to acoustic directionality. The Penn State team has developed new sound-absorbing materials that, if integrated properly, improve sound insulation and reduce sound reflection. These materials have been designed to absorb certain sound frequencies, reducing the reverb effect and optimizing the quality of communication within each sound enclave. The use of high-performance materials in combination with diffusion technologies allows for more precise management of frequencies and direction of sound, improving the overall acoustic quality of the environment. Real-time acoustic control systems. Another key innovation in the audible enclaves is the use of dynamic acoustic control systems that allow for real-time adaptation of sound management within spaces. These systems use acoustic sensors and artificial intelligence algorithms to monitor and adjust sound conditions according to changes in the environment. For example, if a person enters an area, the system automatically adjusts the volume and directionality of the sound based on the location, improving the user's experience without disturbing others. Practical applications of the audible enclaves. The potential of the audible enclaves is enormous, and their applications extend to numerous sectors. The following are some of the main areas where this technology is being applied. Public and commercial spaces. Public environments, such as museums, galleries, railway stations, or airports, are places where sound management is essential to improve the visitor's experience. Audible enclaves allow you to create isolated sound paths for different sections of a museum or the various areas of a station, reducing noise pollution and increasing the effectiveness of communications. Open space offices and work environments. In modern open space offices, background noise is a major distracting factor. Thanks to the audible enclaves, it is possible to isolate specific work areas, creating acoustically separated environments that reduce noise interference to a minimum. People can work in an acoustically optimized environment for their productivity, without being disturbed by the surrounding sounds. Theaters and auditoriums. In performance environments, such as theaters, auditoriums, or stadiums, sound management is crucial to ensuring good audio quality. The audible enclaves can be used to precisely direct sound to the audience, improving clarity and intelligibility while minimizing noise interference from other areas or from the audience. Healthcare environments and hospitals. In the healthcare sector, Audible Enclaves offer the advantage of creating acoustically insulated spaces where patients can benefit from a quiet and controlled environment. At the same time, it is possible to ensure that important messages are conveyed clearly in the common areas without disturbing other areas. Conclusion: the future of Audible Enclaves. The Audible Enclaves represent a true revolution in acoustics. Using advanced technologies such as directional acoustics, computational acoustic modeling, and real-time control systems, the Penn State University team has developed a technique that can optimize sound with extreme precision. With applications ranging from architecture to medicine, from artistic performance to public space management, Audible Enclaves have the potential to transform the way we conceive and experience acoustic spaces. The adoption of these technologies could, in the future, lead to a fully customized sound experience, where each individual is able to enjoy the sound optimally without being disturbed by the surrounding context, paving the way for a new paradigm in sound engineering.